Okay, welcome back to a new week. So we're going to continue with functions and relations, and definitely try and finish the slides today. Okay, so we stopped down here talking about different kinds of relations. They can be reflexive, symmetric, transitive, and there were some anti-words up in there too. Let's move on now to a topic that looks different, but is secretly quite similar to relations. Okay, so this is called a directed graph, and it is another example of how in math you can formally specify how to draw pretty pictures. Okay, it's all very graphical. So a directed graph, and sometimes we say digraph for short, it's just a pair of two things. It needs two things to make a graph. It's a vertex set and an edge set. Okay, so here is a graph of all the places you can go from Fresno, right? Kind of. You can go to LA, you can go to SLO, and then Santa Barbara's on the way if you keep going south, and then you'll also run into LA, right? And then you could also go up north, San Jose, before San Francisco, assuming you take the 101. Okay, so that is a graph. That's all it needs. All you need to specify a graph. You give the vertices, which is all the places you can go. So a vertex is all the places you can get to. So like San Francisco's a vertex, Fresno's a vertex, LA's a vertex. Those are all vertices. Okay, and so you have to supply a set of those. That's part of the graph. All the places you could potentially get to. And then you give all the ways you can get there. Okay? You give a set of edges, and each edge, you see, each edge is a pair. You see that? It is itself a pair of two vertices. So like this edge right here is Fresno, LA. Yeah? That's the idea. And so that is all you need to specify this picture. Okay, I guess like the placement doesn't really matter. I could like move Fresno way over here if I wanted to, and it would still be a graph, but I tried to keep it kind of map-like. So that's all a graph is. It's a place, it's a set of vertices, all the places you can go, and then a set of edges, all the ways you can get between places. So Fresno, you can go from Fresno to San Jose, to SLO, or to LA. You can't go straight to Santa Barbara, okay? You kind of have to pass through SLO, at least in my graph here, okay? There's probably a fancy road you could take otherwise. Okay, so that is directed graphs. Are you ready? Let us continue. So they're really good for representing relations, right? We've technically been drawing everything like a graph already, secretly, yeah? It's just now we can give names to these little places that you can go. Okay, that's all it is. And really good for like representing roads and cities and all that kind of stuff. Like deep down in Google Maps, it's just a big directed graph of all the streets. That's how it moves you around to places and like finds the shortest distance so that you can get there as fast as possible, right? So yeah, digraphs are quite nice, and it's very natural to move around, like we were saying. You can go places like Fresno, you can go all the way to LA, taking the scenic route, okay? That is how you can move around. You can move around by following these edges, and when you follow a bunch of them, you draw what's called a path, okay? That is indeed the technical term. Here's a path from Fresno to LA. Here's another path from Fresno to LA. Okay, there's two different ones I could find here. So, yeah, these are just some new terms. Graphs. They're useful, and we're going to study them in their own chapter soon. Okay, but this is a good head start because it's very similar. This is essentially a relation, but now the little dots have names, right? Okay, that helps us what's called compose relations now. So remember that we can compose functions. You can think about composing relations kind of as like making paths of a certain length in a graph. So don't worry about that if it's too confusing. I'm going to explain it in a different way too. So you can compose relations. So let's say you have R and S. You can compose, again, S after R. Yeah? Compose S and R together. And Both of those relations need to be on the set A, the same set, of course. Otherwise, this doesn't make sense because you can't like relate A to B, right? You have to like stay in the same set. That makes sense, hopefully. And that should be a comma, I think. And the way that you compose is you say that A and C are related in the composition if and only if you have an A and a B in A such that, we have A, B, and C, excuse me. Let's make this larger so it's all there. If and only if you have A, B in R and B, C in S. So the first thing you do is in R. You're relating A and B by R, okay? So like those are related through R somehow. This is A, this is B. And then S is relating B and C. And you can compose first R then S, right? It's S after R. You can compose in this way and get something in S circle R, S composed with R. Okay, hopefully that makes sense. So you first do R, first you follow things by R, then you follow things by S, and that is the composition. All of those little pairs of things where you have AB and you have BC, where those match up, the B's match up, that means that A and C are related in the composition. Okay, so let's do an example. Here is S, here is R. What is S composed with R? So we have to find all the little places where we have things in common, like A and a B, and we need to find a B over here now. Okay, that's the name of the game, and maybe if I make this smaller, we can do it over here. Yeah, that worked out. Okay, cool. So here is, honestly, how about we draw it? That might make it easier. Let's draw S in blue, because I'm already in blue, and we have, it looks like A, B, C, and D. So we have A to B. We have, and this is under S. A and B are related. Under S, A and C are related. Under S, C and D, and the order matters. Like C is the first thing in the relation, so that's why I'm drawing these directed graphs. Yeah, and then C to A, also related. Okay, so that is S. Let's do R in green, and that's okay. BC. So all the green stuff is R, and I'll draw it in S later. BC, CB, cool. This one goes backwards as well. AD. So I kind of want to draw an arrow like this. That's kind of ugly, but sorry. It's going to work. And DB. Okay. So that's R, and this is S. Okay. So I've drawn the relation in graphical form, and now we need to compose these relations. So what is S composed with R? So you need to find R and then an S. Okay, find where these things match up. So if we just follow the definition, we'll notice that, okay, A and B, those can match up with B and C. So definitely we have, oh, I'm sorry, it's R first. We have, let's see here, B and C and D. So that means we have BD in the relation. Okay? So we have BD in the relation because we do the BC first, and then we match up on the C's, and then we take the first thing and the last thing. And that is in the composition of the relations of S and R. Okay, so we have BD, and let's notice how we can find that. It's follow a green thing, then follow a blue thing. Okay, so how do we find that here? Well, all right, we start at B, we did a green thing. How about this one right here? And then we did a blue thing. How about this one right here? And so that's how we can find, in the graphical form, all of the compositions as well, okay? All the different new relations. So BD is a thing. Okay, how about, does anything else start with C here? Yeah, BA is also a thing, see? Because we can use this one and this one. This one first, then this one. We have BA. Okay, this one first now. What starts with B? Nothing starts with B, so we can't use that for anything. Okay, how about this one? What starts with D now in S? Nothing, we can't use this. Okay, darn. How about this one? DB. So we have to find something in S that starts with B. Darn. Again, nothing starts with B. So it looks like the composition is only BD and BA, and we can confirm that. It's follow a green thing, follow a blue thing. Well, this green thing has no blue things to follow after it. This green thing, you could go straight here. That makes sense. So that's our BD. What else could we do? We can do BA as well, using that same one. Okay, how about this one? Well, again, there's no blue things coming out of it. Can't use it. And same for this one. No blue things coming out of it. We can't use it. So that confirms that this is the composition. Okay. If I want to make this very, very horrible, I guess I will. So here's the composition. Maybe I'll draw it in rainbow over here. We have A, B, C, D in the composition. We have B, D related, and then B, A related. Okay. So yeah, composing relations is sometimes useful, and you just line them up. You first follow something in R, so you take the BC, and then you match up the C with something in S, okay? Because then you can go from B to C and then C to D, and that's the composition. Okay, just watch out that R needs to be done first, even though it's on the right side. Okay, hopefully that made some sense. That is composing relations. All right, and yeah, just I think I hinted at this enough. Composing a relation with itself, composing a relation with itself is something different, and what that does is it finds all the length 2 paths that exist in the relations graph, which is fun to think about. So if you just had one relation, and you compose it with itself, like green with green, it's all the length 2 paths you can find. And so like this and this, there's a self loop now. So that's not something I want to get into. It's just a fun little tidbit there. Okay, so that's composing relations, and that brings us to closure. Okay, so we like when relations are reflexive, symmetric, and transitive. A lot of cool relations like less than and equal to have some of these properties, and we like those properties. Yeah. Maybe we have a relation that's not yet one of these things, but we would like it to be one of those things. So there's an idea of closure now, and I'm going to define everything on this slide and then give examples on the next. So the idea is you can create the smallest relation that's the same as your original relation R, but it also is either reflexive or symmetric or transitive or all three, depending on what you want. So now for the term, when you modify your original relation to be blank, so maybe reflexive, you have then created what's called the blank closure, the reflexive closure of R, okay? And same for symmetric and transitive. So if you want to create the reflexive closure of something, of any relation, you just make sure that you add self loops in for every element in the domain of the relation. You just make sure that X is related with X. That's all. So for example, the reflexive closure of strictly less than is, okay, go and make sure that everybody is related to themselves now. Oh, that's just less than or equal to. You see that? That's interesting and fun to think about. Okay, symmetric closure, also very similar. If you have X related to Y, in order for this R to be symmetric, you need to have the other one too. So if you don't have it already, go and add Y related to X in that order. Okay? So hopefully this makes some sense. It's just make your relation be this property, okay? So for transitivity, if you have these two things, it's kind of like composing relations. Oh man, you just take this one, and if you also have this one where they match on the middle thing, you go and add X related to Z, okay? And you keep on doing this until there's nothing left to add, because maybe once you add X, R, Z, you can find more transitive things that you need to start adding, okay? And I'll show you examples of this, don't worry. And then in terms of graphs, which is quite nice, you just keep on adding x related to y if there is a path anywhere from x to y in the original graph. That's fun to think about. Okay, so yeah, I'm going to give you examples on the next slide, don't worry. But this is reflexive closure, symmetric closure, and transitive closure. So closure is a nice thing to have, or to be able to do. Okay, so I stole this relation from the book. Here it is. 1's related to 2, 2's related to 5, 5 is related to 4, 4 is related to 3. That's the original relation R, okay? What we're going to do now is find its reflexive closure first. So let's modify this to be reflexive. So what does it mean for a relation to be reflexive? You got to add x related to x for everyone. So this is the reflexive closure. Do you see that? Boop, 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 just like that. That is the reflexive closure. Isn't that nice? Not too bad. So yeah, that one was easy. Check. Symmetric closure now. Symmetric closure means, okay, if we have x, r, y in the relation, we need to go and add y, r, x if it's not there. Okay, so for example, we have this one, 1's related to 2. We also need to add 2's related to 1 in the symmetric closure. You see that? That's useful and necessary. So we need to go backwards now. And that is the symmetric closure of this relation. So it's like you can move around and always get back to where you were. Quite nice. Okay. Transitive closure, that's the hardest one. It's if you have x, r, y and y, r, z, you need to go then and add x, r, z. Okay? So for example, here is 1 related to 2 and then 2 related to 5 where they match up on the middle bit. That means I need to go and add 1 related to 5. Do you see that? I can go straight there now. I just follow the path. And so for transitive closure, it's like if there is a path anywhere, you can go straight there. That's what transitive closure means. Okay? Because now I have 1 related to 5 and 5 related to 4. You see how this new one, I can now use it, oh man, to make this one. Yeah? That's the key. You got to keep trying after you add new things. And then now that I added this one, and I can use that one and this one to make 1 going all the way to 3. You see that? I can go all the way around to 3 now. Yeah? And so, again, okay, now I have, let's see here, this one. It goes here, and it also goes like that, where they match up on the 5 in the middle. I have 2 related to 5 and 5 related to 4. So like the 5 is the y. And so I can go straight there now, 2 related to 4. And now that I have this one, I can use it with this one to make 2 straight related to 3. Yeah? And we just keep going. So 5 is related to 4, and 4 is related to 3. Oh man, that means we can go straight to 3. Yeah? That is the transitive closure. I think that's everything. Oh shoot, you know it might not be. Let's take a look here. 5 can go to 3. Dun dun dun. Do we have any loops now? No, I think it's always moving forward. So I think that this is the transitive closure. But let me do a quick little example that makes it fun. If you do the symmetric closure and the transitive closure, like let's pretend this was our relation, just like that. Let's do the symmetric closure of this, which is that, and then also the transitive closure. I can do boop and then boop and get a self loop. Similarly, I can go this way and get a self loop. So if you do multiple closures, you can get cool looking things. And suddenly I got the reflexive closure for free, which is weird to think about. So yeah, that is closure. Hopefully it makes sense. You just take your relation that wasn't symmetric, that wasn't yet transitive, and just make it that, okay? The one where you have to watch out is transitive, because the second you add a new edge, you might have to add even more, okay, using that one. Okay, so that's closure. Now it's your turn. So compute the transitive closure of this relation here. You can either like leave it in simple form, or you can draw the graph, whatever is easiest for you, but give that a try, and then we'll do it together. Okay, so here we have a beautiful relation. Let's just do it out here. Let's do it symbolically first, and then we can make sure that that's true by doing it with pictures. So I have 3 and 4. Do I have a 4 anywhere else? Yeah, I have a 4 and a 3. Okay. So the the transitive closure is going to have everybody that's already there plus the stuff that we add now. Okay, here's the new stuff. I'll put that in green. So 3, 4, 4, 3. So we have 3, 3 now. Yeah, that's nice. Okay, we have anything else match up with a 4? No. How about 2, 7? Does anything have a 7 in front? No. Okay. How about 1, 2? Does anything have a 2 in front? Yes, 2, 7. Okay, so we can do 1, 7 now. Okay, 1, 7. Anything else have a 2 in front? No. Okay, 4, 3. Does anything have a 3 in front? Yes. We have, let's see, 3, 4. So now we have 4, 4. Anything else have a 3 in front? We have 3, 3, but that would again give us 4, 3. We don't need to add that again. Okay, so that's quite nice. Okay, how about these? I think we already did the 3s, but do they change at all now that we've added stuff? We always need to check again. Okay, 3, 4. Anything have a 4 in it? Well, we now added this one, but you can still go straight there. Let's see here. Anything else? How about this one? 3, 3. That doesn't change anything. 1, 7. Does anything start with 7? No. We're good. 4, 4. And just as a hint, if you ever have things related to themselves, composing that or doing the transitive closure is not going to change anything. So I think that this is the transitive closure. Let's confirm this with pictures. Okay, so we have 1, 2, 3, 4, and just 7, right? 3, 4, 2, 7, 1, 2, 3, 4, and just 7, right? So 1, 2, 3, 4, and 7. Okay, so we have, originally, I'm just going to draw the original one, 3, 4, 2, 7, that's getting ugly, sorry, and 1, 2, and 4, 3. Bam. So now, I think the graphical form is easier, because now you can tell, like, okay, it makes sense. I need to know, I need to now add, I can go here and then here. I need to add 1, 7, definitely. I need to add 3, 3, so I can go here and back. Same for 4, go there and back. And that's about it. These are, like, not connected to anything else. This is all well and done. Everybody's happy, so I added 3 things, and it's obvious now why there are only 3 things to add. Okay, so that hopefully wasn't too bad. And if you need to write it out, remember you include the original relation in the new one, that is the transitive closure. Okay, so that is that. And now we're ready for a very, very important concept. Okay, we had to mess around with all these silly terms to get here, but it's very, very nice now that we're here. Okay, so you're ready for what's called an equivalence relation. Okay, so when you have a relation R, we say that it's an equivalence relation if it is reflexive, symmetric, and transitive. Okay, it has to be all 3. And why in the world might they call it this? What is a good example of a reflexive, symmetric, and transitive relation? Oh darn, it's equality. Equivalence. Because 2 is related to 2. 2 is equal to 2. Yeah? If x is equal to 5, then 5 is equal to x. Symmetric. Also, x is equal to x. Transitive. Oh man. Wonderful. Yeah, that makes sense. Or I was doing the transitivity part of this. Maybe I should just spell it out. If x is equal to y and y is equal to z, then yeah, obviously x is equal to z. Yeah? Those two come together. So, yeah, we have things that are equivalence relations now. They don't have to be equality, but they behave like equality in a sense. Okay, that's why we call them equivalence relations. So your book's going to use the squiggle, the tilde character, when A is related to B and R is an equivalence relation. So you can read this as, it's not just related to B anymore because it's an equivalence relation, it's equivalent to B. Okay, that's how we can say that. So this is the idea. Any element that's linked together by an equivalence relation they are equivalent to one another. Okay, those two elements, they are equivalent to one another, to each other. And so usually we just talk about all of those things that are equivalent at once, because they are, for all intents and purposes, the same thing. Okay, so for example, here is an equivalence relation. Boop, boop, and boop. It's reflexive, it's symmetric, it's transitive. And the idea is you can move around to anywhere in these groups. Okay, so all of these blue things are equivalent to each other. They're equivalent to themselves, of course. They are equivalent to this one and equivalent to that one. And you can move around to anybody. They all have paths to each other because they're all equivalent. They can all get to each other. And also straight there, right? So they are equivalent. They're all related to each other. Okay? Similarly, these two green ones are also equivalent. They're related to each other. Okay, we can always get to them, and they're, of course, equivalent to themselves. And then this red guy out alone, sadly, is only equivalent to itself, but it's still an equivalence relation. This whole thing is an equivalence relation. Okay? So this is why we say that, we want to talk about things all at once, because it doesn't matter which of these blue things you have, they're all equivalent, and they can all be substituted in for each other because their properties are the same, okay? All the blue things have the same property, okay? At least as far as the relation is concerned. So that means they're all interchangeable, okay? They're all interchangeable. Just like if you had x equal to 5, you could say x everywhere, or you could say 5 in its place, and nothing would be any different. They are equivalent. They are replaceable. Okay? So for that reason, we like talking about what's called equivalence classes, because we want to kind of like smush all the blue things together, all the green things together, all the red things together, because they're all equivalent to themselves. Okay? So for example, if A is the domain of the equivalence relation, so all of these dots are pieces of A, and A is in A, then we can say bracket A bracket. That's called the equivalence class. Okay? That is an equivalence class where you're using A to get everything that's equivalent to A. Okay? So in math, this symbol is giving you back the set of all things that are equivalent to A. Okay? All the other things that are equivalent. So for example, if I started numbering these, like this was, that was 1. Does that work? 1, 2, 3, 4, 5, 6. Well, the equivalence class based at 1 is equal to 1, 2, and 3. It's all the things that are equivalent to 1, which is including 1. And notice that this is the same as the equivalence class based at 2, the equivalence class based out at 3. Interesting. It's all the things that are equivalent to this thing, okay? To the 2, to the 3. And they're all the same. It's all the same set. 1, 2, 3. Yeah? So, yeah. This is called the equivalence class. The equivalence class using 1 is 1, 2, 3. The equivalence class using 4 is 4, 5. Yeah? Same for the equivalence class using 5. Okay? And the equivalence class using 6 is just itself. Okay? So all of these things, from the point of view of the relation, are equivalent. So we call them equivalence relations and equivalence classes. Okay? So hopefully that made some sense. It's an interesting little term, and it's really nice to have when you have an equivalence relation. Okay? Equivalence relations do some really, really nice things. They split up their domains. They split them up into each of these classes that don't touch each other. You see that? They do not touch each other, because otherwise, if they did, because it's reflexive, symmetric, and transitive, they would be in the same class otherwise. Oh, very nice. So, yeah. Remember, the definition of partition, that's it when you can put a set and break it down into a bunch of little subsets that are disjoint and whose union is the whole thing. Remember the definition of pairwise disjoint, right? They don't overlap. The idea is that equivalence relations partition a set. And that's a great way to break down a set if you have an equivalence relation on it. Okay? So partitions are useful, and the reason that you can't get from one to the other is the second you added like a new relation between equivalence classes, they would merge together to be the same equivalence class. Okay? So this is the blue equivalence class. This is the green equivalence class. This is the red equivalence class. They don't touch each other. They're not related. They don't speak. Okay? It's unfortunate, but that's how it's working. Okay, so we're now ready for you to give it a try. So I want you to figure out if the following relation, R down here, it's defined to be this. Tell me if it's an equivalence relation. Okay? Tell me if it's an equivalence relation, and that means you just have to check these three things, right? Check that it is both reflexive, symmetric, and transitive. All three of those things, okay? So give that a try, and then we'll do it together. Okay, x minus y equals 3m for some integer m. What in the world does that mean? So let's give some examples of things that are related to see if we can come up with like what's going on here. So let's pretend that m is 1. Let's pretend that m equals 1. Let's see what's related. It looks like, okay, something minus something is 3, so like 6 and 3, and 4 and 1. Yeah, that makes sense. So they're just 3 apart. That would make sense. Like 7 and 4. Okay, if m equals 2, we have, let's see here, dun dun dun. We have things are related if they are 6 apart, and the first one's the bigger one. So like 6 and 0, right? And then we have, let's see here, 7 and 1, etc., etc. 8 and 2. Okay, that makes sense. So we have a good idea of what it's looking like now. Some weird relations going on between these numbers, but that's okay. We need to figure out if this is an equivalence relation. Okay. So let's do this. Is it reflexive? Let's ask ourselves, is it reflexive? That means that no matter what number you have, it's x is related to itself, okay? Sorry, x is related to x, okay? No matter what x is. So let's see if that works. Is it true that x minus x is equal to 3m for some m? Can I pick an m that makes sense here? And the answer is yes, I can pick m equals 0. So yeah, reflexivity checks out. Ooh, okay, that's not too bad. How about symmetricity? If I want to know that this is symmetric, I need to know that x minus y equals 3m. If I have something that's related like this, x minus y is equal to 3 times some m, I need to know that y minus x is related. So it's equal to 3 times some other number, like m2. This is m1, this is m2. Is this true? And the answer is yes, because I can take whatever this m1 was, multiply it by -1, okay? So if I do this, if I multiply this whole thing by -1, I get y minus x, right? They flip-flop, equals 3 times -m1. And I can use this -m1 as my m2. And it'll work out. So symmetricity checks out as well. Ooh, 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 this is quite nice. Now we need to try for transitivity. We got to figure this out. We need to know, or we need to figure out if we know that this is true. If we know that x minus y is equal to 3m for some m, or m1, we also know that y minus z is equal to 3m2, we need to figure out if it's always true that x minus z is equal to 3m3 for some new integer m. Okay? They don't have to be the same. They could be, but they don't have to be. We need to make sure this is always the case. Interesting. Let's figure this out. Okay, so this is the idea. So we know that x minus y is this and y minus z is that. Can we somehow figure out, can we somehow use these equations to make this equation happen? And the answer is yes. What if we add these two? Add these two equations. We add the left side, we add the right side. The y's will cancel. X minus y plus y minus z. You see that? These two sides and the y's cancel. Equals 3m1 plus 3m2. Oh shoot. This might be working. We have x minus z equal to 3 times m1 plus m2. And this is a new integer that could be our m3. What? It's transitive. This is an equivalence relation. Isn't that cool? So hopefully you came up with that. It took some steps to figure that out, but isn't that nice? What is it doing? How are these equivalent then? What does it mean? What does this relation mean? And don't quote me on this, but I think it means this. The way to figure out what an equivalence relation is trying to do is you find the equivalence classes. And here's what I think they are. So what are all the things related to 0? Because they'll be in an equivalence class with 0. Well, it's all the stuff, well, 0's in there definitely, it's related to itself. And okay, anything that's 3 away from that, and then anything that's 3 away from that, 3, 6, 9, 12, 15, 18, etc. On and on and on. And then anything that's 6 apart. These are already here. 0, 6 apart, 6 apart, 6 apart. Interesting. And then the other equivalence class would be 1, 4, 7, 9, 10. All the things that are 3 apart there. And then, finally, 2, 5, 8, 11, 14, dot, dot, dot. So if you would believe it, and I think I've convinced myself that these are the equivalence classes, these 3 things, that's how it's splitting up numbers, it's mod 3. It's doing mod 3. You see that? It's essentially the mod 3 equivalence relation. All the things that are equivalent to mod 3. What? Isn't that the coolest thing? So, yeah, here is how you can define that 2 numbers are equivalent modulo 3. Isn't that fun? And it's an equivalence relation. So, yeah, very unexpected, but very, very cool. Okay, let's keep going. So now we're on to what's called N-ary Relations, which is a fun, long word, but it's nothing new. It's really not. So we have been sticking with relating 2 things. Like, okay, x is related to y. Z is related to w. Just like that. But we can have bigger families than that. We can have a relation on more than 2 sets at once, okay? And all that is it's just a really big tuple. All these things are related, all these n things are related to each other at once, okay? They're related in this way, in this order. Okay, so, for example, you can say that, okay, this x, y, z, and w are in a relation all together, where x is the first thing, y is the second thing, z is the third thing, w is the fourth thing. You can say P, Q, R, S. This could be like a different relation that relates 4 things at once in some way. So it might be hard to wrap your head around why you might want this. So let's talk about programs. We're good at programming, right? So you can actually model input and output of computer programs, computer functions, right? Functions/programs as N-ary relations. Oh, dang. And my simplest example for you comes from append in Racket, where you take 2 lists and you build a bigger one by just shoving them together. So you get, if you append 1, 2, 3, and then 4, 5, 6, you get the bigger list, 1, 2, 3, 4, 5, 6. And so you can define an append relation where this is true. They're related in this way. X, Y, and Z are related if they're lists and append of x, y is equal to z. So here are some things in that relation. You have, let's go back to blue. You have the lists, I don't know, 1, 2, and the list 2, 3. They are related with this third list, okay? That is the list, that is their concatenation, 1, 2, 2, 3, yeah? So that's one thing, 1 3 tuple of lists, of racket lists that are in this relation, okay? Another one is, I don't know, you can have just 1 and like just 42, and that gives you the list back 142. So they would be in this 3-ary relation, yeah? So it's just, it's not too bad. These 3 things are related in this way, if they're lists and the append of the first 2 equals the third one, yeah? So this is how you might want to use relations later. If you get into a fancier programming class in upper division, once you go to a 4-year college, you'll talk about maybe relational programming, where you think not in terms of input-output at the function level, but input-output at the relation level, which is very, very interesting. So yeah, do come to office hours if you're interested in that, and I can tell you more about it, but that's where I want to leave you there. It's just, you can relate more than one thing. That's all I wanted to say on this slide, okay? Not a big deal. And so finally, here's an example for you just to make sure that you're understanding it. Here's a relation that relates 4 numbers, and they're all positive integers, and we say that they're related in this order if a plus b plus c plus d equals 6. So please, in roster format, tell me what the following relation is, yeah? And so remember, it's going to be a set of a bunch of 4 tuples, okay? Quadruples, if you will. So let's give that a shot. So R equals, well, it's a bunch of 4 tuples where these things add up to 6, and they're positive integers, so I can't use any number smaller than 1. So like the smallest one is 1, 1, 1, 1, and then I'm forced to put here 3. You see that? And then similarly, you have to do 1, 1. If I want to make this one bigger, I can make it a 2. That makes this now have to be a 2. Then I can do 1, 1, 2, oh, sorry, 1, 1, 3. That would force this to be a 1 now, yeah? And so I won't bore you with the rest of this. I'll just go write them out and come back. But I think you get the idea now if you weren't able to get it yourself before. Give it a try. Okay, so here's the final answer. And yeah, it's just all the things that add up to 6. And if you wanted to be cool, you could write a program to do this. And I was lazy, so I didn't use racket this time. I just wanted to check myself, so I did it in Python. But here, if you're interested, it's just a huge quadruply nested for loop, yeah? Just check if those numbers that were your variables add up to 6, and then print them, yeah? And so then it gives you all the numbers. Okay, so yeah, that's all I wanted to show you there. You're now experts at functions and relations. Probably the most important example that, or the most important term that comes out of this is an equivalence relation. You'll see that a lot, as well as closure. That might come up in an upper division algorithms class. So those are very, very important things. Actually, I might have lied. Graphs are probably the best of all 3 of those. You're going to see graphs for the rest of your life, no matter what you're doing, especially if you're going to become a programmer. And yeah, that's all I got for you. So I will see you in the next lecture. We have officially finished these slides, and so we're going to start some new ones now. So I'll see you then.